Of course, the piston, rings, and cylinder work in combination. As the pressure from combustion increases, the piston is forced downward in the bore. During the power stroke, the top ring is forced against the cylinder wall. High pressure is directed both outward, helping to seal the ring against the wall, and downward, forcing the ring onto the bottom of the groove in the piston. The term cylinder bore is nothing more than the round hole the piston rides up and down in the engine block. More important to us than the shape of the cylinder is the cylinder wall. The term cylinder wall describes the finish condition of the cylinder, a very important component. The two common finishes that are used on Briggs and Stratton engines are crosshatch and diamond bore. Each is finished with a pattern of peaks and valleys that become pockets for oil, preventing metal-to-metal contact. The peaks are called asperities. The average height of an asperity is 8/100,000ths of an inch. I doubt there is a measuring tool in your toolbox that can measure that tight a distance. When new from the factory, the higher asperities can cause metal-to-metal contact with the rings. However, during the break-in procedure, the piston rings plane off the peaks and produce a working surface. If a peak is broken and drops between the piston skirt and the wall, light scratching may occur on the wall or the skirt. This is normal to the break-in process. Scratches are more noticeable on engines with softer aluminum surfaces, like the cool-bore and diamond-bore engines. The three rings on Briggs and Stratton pistons are the compression or top ring, the wiper or middle ring, and the oil control ring, the double ring at the bottom of the piston. The compression ring prevents expanding gases from getting by the piston. It, like the other two rings, rotates while the engine is running to wipe away the combustion residue within the ring lands. Combustion residue and shellacs can interfere with the ringland seal, as well as causing rings to stick. A clean, flat ringland surface is particularly important to the compression ring. Most of the oil that gets past the compression ring does so between the ring and the land in the piston, not between the ring and the cylinder wall. The compression ring is sealed against the cylinder wall and piston lands during both the power and compression strokes. A worn ring or a poor seal during combustion and compression does not directly cause oil to get past the rings. However, it results in a loss of crankcase vacuum, lower power, and hard starting. It is the intake and exhaust strokes that are responsible for oil getting into the combustion chamber. Without pressure against the compression ring, the oil mist from the crankcase gets past the ring through the ring groove. This is what causes carbon buildup in the groove of the top two rings. The oil working its way past the rings through the grooves during the exhaust and intake strokes is burned during the power stroke. To maintain compression, the sealing point of the ring against the groove face is extremely important. Either cylinder or ring wear can move the point of the seal. One engine may have the same wear above the reject standard as another, yet not emit smoke from the exhaust. The difference could be in the piston and ring package, and more specifically, where the rings seal in the groove. The wiper ring provides a controlled film of oil to lubricate the compression ring. It also contributes to resisting blow-by past the piston. The wiper ring typically has a tapered face, so that the knife blade shape will scrape the oil down the wall to the oil ring. Wear of the wiper ring reduces engine performance, just like wear to the compression ring. As it wears, however, it allows more lubricant to be left on the cylinder walls. If installed upside down, the wiper ring scrapes the oil upwards. If enough oil collects, the compression ring can be hydraulically lifted off the lower land. If the ring end gap is tighter than the compression ring, blow-by pressures can build up between the two rings with similar results. The oil control ring contacts the oil thrown up by the lubrication system and the crankshaft. It wipes away large volumes of oil. Its double-edged, slotted design allows large amounts of oil to flow away from the cylinder wall without causing any excess drag on the piston. Ports toward the ring groove wall or channels cast in the piston skirt also help quickly remove large quantities of oil. The oil control ring adds little to the compression generated by the compression and scraper rings. It only affects compression if it is broken and damages the cylinder wall.